When we're looking at business, one of the things we want to be able to do is we want to minimize our cost or minimize perhaps the time we have to spend, and we want to maximize things like profit and revenue. We've looked in the last couple of sections at things like the first and second derivative and how they can help us determine maximums and minimums of a function. Today, we're going to look specifically at business-related examples and how maximums and minimums can be determined for those. One of the things we're going to look at is minimizing inventory cost. The inventory is the product that you have. And so when we model inventory using a function, we want to ease the process a little bit. And to do this, we're going to make it more approachable by making a few assumptions. We're going to assume that we know how much we're going to sell for the year. We're also going to assume that we sell the same amount every day. That keeps our inventory declining at a linear rate versus having to make a complicated function for our inventory that's currently accessible. And we're also going to assume that we always order the same amount of product and we always order it the same increment in time. So we order 100 items every 6 weeks. We're not going to change that. These assumptions help us create a graph such as this, where we have our inventory, the amount we have in stock, versus time. Notice here the X is what we call the lot size, or how much we order at any given moment. So when time starts, we make that first order of X items. They come into our storage facility. And then every day we sell a few and it declines until we hit this point and it's time to order again. And then it declines and it's time to order again, and so on. At any given day or moment in time, we can have an average inventory here because, again, it's declining linearly. To make sure that we know our cost, we know that the two things affect the cost of our inventory. Our cost is affected by how much does it cost to store all these items that we've ordered? Do we have to have a refrigeration facility? Do we have to have a storage warehouse? And also, each time we order new things, how much does it cost us to ship? Because we could very easily order everything we need to sell for the whole year at the beginning of the year, but then we'd have to pay to store it until it's sold out at the end of the year. To make these calculations now, the storage cost is going to become the storage cost per item times the average inventory, because that's the average of what we have at any given moment. And then our shipping cost from the cost per order times the number of orders that we make. And we calculate the number of orders that we make by taking the total number of items that we order and dividing by the number of items that we order each time, or the lot size. Let's do an example. If we have a furniture dealer that sells 500 desks in a year, they could very easily order 500 desks at the beginning of the year, but then they'd have to pay to store them. And this particular furniture dealer knows that it costs $6 to store each desk. And they also know that each time they order more desks, they pay a $60 flat fee. So not $60 per desk, but just a $60 flat fee. So we want to figure out how many times per year should they order, and what number of desks should they order each time they order to minimize inventory costs. The key word here is minimize. And so eventually what we know is we're going to want to take the first derivative of this cost function. As already mentioned, the cost function is calculated by the cost of the storage, which in this case is $6, times the number of items, which is our average inventory, plus we take the shipping cost, or in this case, the flat delivery fee, times the total number of items that we're going to order, divided by the number that we order each time, or that lot size. So when we multiply this out, we end up with the cost function is 3x plus 30,000, and I'm going to go ahead and bring that up, x to the negative 1. This is our cost function. We want to minimize our inventory cost. So I'm going to take the first derivative, which leaves me with 3. This negative 1 gets brought up front, minus 30,000 x to the negative 2. And to minimize that, I know that a local max or local min occurs where the first derivative is 0. And so I end up with 3 equals 30,000 over, I'm going to move that x squared to the bottom. Then I can multiply and I get 30x squared equals 30,000, or x equals 10,000. X squared equals 10,000. So X is either plus or minus 100. Now ordering a negative 100 desk doesn't make sense. So I know my lot size is I'm going to order 100 desks. And if I need 500 for the year, then that means I will order 5 times. And if you were to graph this cost function, you would see that it looks something like this, with this being our minimum cost. So this is representative of our cost function. Something else we may want to do is maximize revenue. Notice we're talking here about revenue, not profit. If I know I can sell 440 donuts a day at 50 cents a donut, and I know I sell 40 fewer donuts every time I raise this price 10 cents, what price should I sell donuts for to maximize revenue? Well, let's consider our price is a function that is changing as well. The original price is going to be 50 cents, but my new price is going to be 50 cents plus 0.1 times some variable, however many times I'm going to raise the cost of that. And so then I can also calculate the number of donuts I'm going to sell. And the number of donuts I'm going to sell is going to start out at 440, but then my sales are going to return to 440 minus 40 donuts times however many times, notice these are the same value, I raised the price. Now, in order to determine our revenue, we know that revenue is going to equal the amount sold times the price. If I am selling donuts and I sell 10 donuts and they're 50 cents a piece, I just do 10 times 0.5. Well, here my amount sold is this 440 minus 40x, because it depends on how many times I raise the price, times my price of 0.50 plus 0.1x, because my price is going up, my sales go down. This gives me a revenue function then of 220 when I FOIL this out, plus 24x minus 4x squared. I wish to maximize my revenue, which we know is directly related to that first derivative, giving me a function of 24 minus 8x. The price 3 times by an increment of 10 cents. So my new price is going to be 80 cents. And my actual revenue, then I can plug into this function. Remember, my revenue is based on the number of times I raise the price. I'm going to sell 320 donuts and my revenue will be $256. Now note, just because the revenue is maximized does not necessarily mean that my profit is maximized. And we can also be sure that this is a maximum because we can take the second derivative, which is going to give us -8, and note that that's less than 0, which tells us the function there is concave down, which does tell us it's a maximum. Demand functions, sometimes we make the assumption that they are linear. And if you remember, that demand function can also be used to help us determine price. So therefore, if we know the demand function, we can get the revenue function by multiplying and if it's linear, all we need is 2 points to determine the actual revenue function. Let's consider an example here where we're selling 3,000 calculators at a price of $7. And if that amount goes up to 6,000 calculators, then the price lowers to $4. I can max out at making 7,000 calculators in my factory. So if the demand function is linear, and this is a key phrase here, how many calculators should I produce to maximize revenue? Notice here the number of calculators is our X value. So I have 3,000 calculators when I sell for a price of $7, or I have 6,000 calculators when I sell for a price of $4. Using my formula for slope, I can do 7 minus 4 over 3,000 minus 6,000, resulting in in 3 over negative 3,000, or a slope of negative 1 over 1,000. But I want this in terms of a linear function. I'm looking for the function that describes price as my demand function. So that price is going to be negative 1,000 times however many calculators I sell plus some y-intercept. I can use either of these points to plug it in. If I plug in a price of $7, that resulted from selling 3,000 calculators. When I multiply this out, I get 7 equals negative 3 plus b. I add 3 to both sides, and so my intercept is 10. So my linear function for price is therefore negative 1 over 1,000 x plus 10. Remember, this is the price, and this is the number sold. And so I am looking to maximize revenue. So my revenue function is the number I'm going to sell times the price, which gives me a revenue function of negative x squared over 1,000 plus 10x. And to maximize that revenue, I'm going to take the first derivative, which results in negative x over 500, because again, I'm bringing the 2 down. 2 over 1,000 is 1 over 500. And then plus 10, I want that to equal 0, which gives me 10 equals x over 500, or x is going to equal 5,000. And so when I sell 5,000 calculators, I can then calculate my revenue to get a maximum revenue of $25,000. Now, in this previous example, that's maximizing revenue. What if I wish to maximize profit? If I know the cost, then I can calculate my profit as revenue minus cost, which in this case gives me negative 1 over 1,000 x squared plus 10x minus 5,000 plus 3x, which gives me negative 1 over 1,000 x squared. When I have 10 minus 3, I get plus 7x minus 5,000. And then again, if I am looking to maximize profit, I'm going to take the first derivative of that. I'm going to bring this exponent out front, which gives me negative x over 5,000 plus 7. I wish to find where that is equal to 0, giving me 7 equals x over 5,000, or x equals 3,500 calculators. Notice that I needed to sell 5,000 to maximize revenue, but my maximum profit comes when I sell 3,500. I can then take that and plug it into my price function or my demand function. And when I sell 3,500 calculators, that is indicative of a price of $6.50. And if I were to graph these two functions, you're going to see that your revenue function was a curve and your cost function was linear. And where their difference is the greatest is going to maximize your profit.